And thanks very much to the organizers for bringing me here to this great place. For me, this meeting is particularly interesting because it gives me the opportunity to meet for the first time people whose names I have known for long, but I have never met before. And so far we have seen many things. We have seen Lessing squares, design, Francis theory and extremal graph theory, hypergraphs, combinatorial geometry, spectral graph theory. And so now we shall see another branch of combinatorics, enumeration. And this will be kind of a survey talk on determinants and Pfaffians, which certainly are objects of linear algebra in enumeration. A question that I shall pose myself is, why are enumerators, like myself, fascinated by determinants? And one obvious answer is, often determinants solve enumeration problems, and I will demonstrate this, and as well Pfaffians. And one particularly nice thing is that sometimes combinatorics may evaluate determinants. I will show one example. And I should make a disclaimer here. So this survey will be very biased. So probably the question that I'm asking is, why am I fascinated by determinants? And the keywords will be non-intersecting lattice paths, and we shall see what this is. So let me start with an enumeration problem. We take a hexagon with a triangular grid on it, and the question that I ask is, how many rhombus tilings of a hexagon with side lengths ABC are there? And the rhombuses, the rhombi that I allow, are unit rhombi. So that means things like this. There are three types of them. Oh no, this. Okay, so now we have come very close. Here's an example, and maybe I should get rid of the triangular grid. I can see more clearly. So I want to tile this hexagon with side lengths ABC. So in this case, ABC are all the same, but it need not be, by unit rhombi entirely. And how many are there? So now the standard way to solve this problem is as follows. You introduce non-intersecting lattice paths. You set up a bijection with non-intersecting lattice paths. So again, here's my tiling. I place points in the centers of the edges along the lower side and points in the centers of the edges along the upper side. And then I connect these points on the lower side with the points on the upper side by following the tiling, by which I mean that you jump from midpoint of an edge of a rhombus to the opposite midpoint of the edge and so on. And so you see that thereby you will connect these points with these points by paths that obviously have the property that they have no common points, and this is what non-intersecting means. It's a little bit an unfortunate terminology, but at some point it got stuck. So non-intersecting paths that have no common points. And actually I don't like this picture so much because it's slightly tilted. So let's deform it into a rectangular picture so that I have a family of lattice paths on the square and grid. And what I've shown you is really a bijection. If you have given this set of paths, you can go back to the rhombus tiling. This is not very difficult to see. So what I have shown you is that I have converted the original enumeration problem to the following problem. I have some starting points, I have some end points. How many families of non-intersecting lattice paths are there such that the ith path connects the ith starting point with the ith end point, and these paths should not have any common points. So again, here are the starting points, here are the end points. How many possibilities are there to connect the two? So this is the problem, and the solution is given by this multi-author theorem. So yesterday in the lounge there was talk about theorems that are very nice, not very difficult, and but very attractive, and therefore they get rediscovered every once in a while. This is an example. So Colin McGregor had not exactly this theorem, had a continuous, a probabilistic version of this at the end of the 1950s. Bernd Lindström discovered this theorem, actually a more general one that I will show, in 1973, working on representations of matrices. Then in the 80s, this theorem got rediscovered in 3 different communities, not knowing from each other. Okay, so VNO wanted to count tableau plane partitions, and thereby they came across this theorem. Michael Fisher is a famous statistical physicist. He dealt with what he called vicious walkers, which are the same thing as non-intersecting lattice paths. So again, he found this theorem, and then these people are people in the former Eastern Germany, working on combinatorial problems of chemistry, and they also discovered this theorem here. What they considered was perfect matchings of hexagonal graphs, and you can easily see that rhombus tilings, if you go to the dual picture, then you have perfect matchings of hexagonal graphs. Okay, so what does the theorem say? The theorem says that if you have an acyclic directed graph, so in my example, my graph is the square grid, so it has these vertices, and the edges are horizontal edges to the right and vertical edges up. Then you have some vertices in the graph, A1 up to AN. You have another set of vertices, E1 up to EN. And there's a certain technical property. So if you connect starting and end points in the wrong way, then there should always be an intersection. In that case, a number of families of non-intersecting paths, where the ith path runs from the ith starting point to the ith end point, is given by this determinant. And the ij entry of the determinant is simply the number of paths from this point to that point. That's everything. Okay, so this is the theorem. And actually there's also a weighted version of this. That is on each edge you are allowed to put a certain weight, and the weight of a path is then the product of the weights of the edges, and then the same theorem holds. But that will not be important in my talk. So here's a sketch of proof of this theorem. As I told you, it's not really difficult to prove. The point really is to discover this theorem. So you take the determinant, you expand it according to the definition of a determinant. So it's a certain sum over permutations, and here you have the corresponding product of the matrix entries. And then this product you can interpret as families of paths where you connect, where the ith path connects a sigma I with EI. So you can rewrite this as a huge sum over these tuples, a permutation, and then n paths that connect the starting points and the end points according to this permutation. So this is now a huge sum of plus ones and minus ones, and some of the plus ones and minus ones will cancel each other. And what we expect is that those plus ones and minus ones cancel each other, that correspond to families of paths that do have common points. And here is such an example. So this is a family of paths connecting the starting points and the end points in some way. And we have several intersection points. What you do is you look for the last intersection point in some particular order. In my case, I take the rightmost and highest such point. That would be that point. And then I consider the two paths that are going through this point, and I switch the portions of the path that are before this point. So you see that this was blue before, and now it became red, and vice versa. Okay, this is an operation. If I apply the same operation again, then I certainly come back. So this pairs two of these objects in my huge sum. So what can I say about the corresponding permutation? The corresponding permutation here is, so the first ending point is connected to the second starting point. The second ending point is connected to the first end point, therefore 2, 1, 3. This is this permutation. And obviously, since I did an interchange of two paths, these two permutations are related by transposition. Therefore, their sign is different. Therefore, indeed, in the sum, they disappear. Which means that in this huge sum, only those survive which corresponds to families of paths without intersection points. And then if we had, given that we had this technical condition, there's only one way to connect the starting points. I mean, there's only one permutation in such that you can connect the starting with the endpoints, and the identity permutation. And so this determinant is indeed equal to the number of non-intersecting paths, where the ith path connects the ith starting point with the ith endpoint. So let us apply this theorem to our enumeration problem. So if you put coordinates in the right way, then you get these starting and end points. And you see the advantage of this formula is that the ij entry counts paths from a given point to a given other point. And in this graph, directed graph that I have taken, just horizontal and vertical steps, unit steps, the number of paths from a given point to another point is a binomial coefficient. So if you work it out, it's this binomial coefficient. So we get this determinant. Here it is again, and in fact this determinant can be evaluated in closed form. So here's the closed form, and in this case what is actually true is once you have written down the closed form, it's already proved, because you can verify this equality by the so-called condensation method, which really is based on an identity of Jacobi, and so there are two other names attached to it. Dana had special cases of this formula before, and Dodgson really called this condensation and used this for computing determinants algorithmically. So here's the identity. You take the determinant of a square matrix, and it relates this determinant with some of its minors. So this is the minor where you suppress the first row and the first column. Here's the minor where you suppress the last row and last column, and similar for the others. So this is the identity. And you may view this as a recurrence for the determinant if you have a family of determinants such that all of these minors also belong to the same family. which is the case here. So all of these minus, if you say A is this matrix, then all of the submatrices can be again expressed in the same form. And so this sets up a recurrence for the left-hand side of this equation. You just have to plug in the right-hand side into the same recurrence, verify that it's also satisfied, but this is very easy. You check b equals 0, b equals 1, and it's proof. And what I've shown you is a proof of famous formula of Major Percy Alexander McMahon. So this is a theorem that is about 100 years old. He proved the number of rhombus tilings of a hexagon with side length ABC. ABC is given by this nice product formula. So he didn't know anything about rhombus tilings. The words that he used was plane partitions, but these are equivalent objects. So now comes a brief interlude. Combinatorics evaluates the determinants. So I promised to show you such an example. So the problem is evaluate these determinants. So I'm sure that everybody, and actually all linear algebra students of you, should be able to do this. Probably they won't do it in the following way. So here's an example, a 3 by 3 determinant, and I mean everybody knows how to do this. And you get 1, and in fact you always get 1, I claim. And here's the one picture proof. So what I claim is that the left-hand side is a determinant that counts non-intersecting lattice paths in a certain situation. Here's the situation. You take these starting points, you take these endpoints, and now I allow horizontal steps to the right and vertical steps down. So for example, you can easily see if you want to compute the number of paths from the second starting point to the fourth endpoint, then what you do is you do 4 horizontal steps, 2 vertical steps, so in total there are 4 plus 2 choose 2. So that this determinant here really counts the number of non-intersecting lattice paths connecting these starting points with these endpoints. But how should you do this? So for example, I have to connect A0 with E0, obviously. Then if I start at A1, I can't go down because then I have an intersection point, so I have to go right, and then I have to connect with this point, and then this leaves just one possibility for this and one for this, and so there's just one possibility, and therefore it's 1. So that's the one picture proof of this determinant evaluation. Well, obviously this is very nice, but usually it's the other way around, namely that you have an enumeration problem and you obtain a determinant, and then you have a hard time to evaluate the determinant. So I promised to show you the general form of the non-intersecting lattice path theorem as Bernd Lindström had it. And here it is. You have the same situation as before. The only thing that I skipped was this technical condition. I throw it away. Then I don't have the same theorem, but instead what I have is that the determinant, as before, is now equal to a sine sum of what? So this P plus A sigma to E, this is supposed to mean the number of non-intersecting lattice paths connecting, where the I path connects A sigma I with EI. So now so here I allow that starting points and endpoints are connected in a different way, but it should be done in a non-intersecting way. The proof is exactly the same. The only question is this good for anything? And I would not pose this question if the answer would not be yes. So here is an application of this general form. I consider a generalization of McMahon's problem, namely, I take again a hexagon, and now I punch a hole, a triangular hole in the center of the hexagon. And now I try to apply the same technique as before. That means I introduce non-intersecting lattice paths. So just for the sake of variation, now my paths go from this side to this side. But you see also that since we have this hole in the center, two of the paths have to arrive at the hole. So 2 because the size of the hole is 2. Okay, so again I take these paths, I deform them so that I have nice paths on a square grid. And now you see the situation is as follows, that I have starting points which are not aligned as before, but there are two special starting points and the endpoints are aligned. And what I want to do is I want to count all possibilities to connect these starting points with the end points. Okay, so in principle this is exactly the situation that is covered by our theorem, with the small exception that depending on the permutation how the starting and endpoints are connected, I have to put a sign. Well, you can think for a few seconds or minutes to convince yourself that in the case that these special starting points have an even number, so for example here I have 2, this is an even number of these special starting points, then no matter how you connect the starting points to the end point, the permutation that describes the connection will always have the same sign. And once it has always the same sign, then again I'm enumerating, and this is what I want. But certainly the formula does not work for me if I would have a hole of size 3, for example. But if it has an even size, so I call the size of the side length of the triangle in the middle I call M, and for the moment it's even. And the hexagon has side length A, B plus M, C, A plus M, B, C plus M. And I plug into the formula for counting non-intersecting lattice paths. I get this determinant. And indeed, now it's not so easy anymore to evaluate this determinant. So actually I should pause for a moment. So yesterday there was a speaker who apologized for showing a really horrible formula. To tell the truth, I didn't really see a reason to apologize for. What I want to say is I can easily beat that. So the number of rhombus tilings of this hexagon with the hole punched inside is given by this big formula. However, I consider this as an extremely beautiful formula. You see, it only involves this H. What is H? H is basically hyperfactorials. It's the product of successive factorials. So since there could be half integers as well, you have to distinguish between two cases, but essentially this H is hyperfactorials, and so this is a totally explicit, compact formula, product formula for this number of rhombus tilings. So if you ask yourself, did you expect that such a formula exists? Probably you would never have thought so. I would not have thought so if somebody would have told me. But that's it. And you may notice that I suppressed the restriction and that M is even. So there's a technical argument that shows that the counting formula is polynomial in n, and therefore the same formula works also for odd m. But certainly I can't use the Lindström-Gessler-no formula for doing this. Okay, so this is a theorem that is about 10 years old. So far I've treated determinants. What about Pfaffians? How do Pfaffians come into the play? So here's another problem. So now I take a hexagon which is symmetric with respect to this symmetry axis, and I want to count all rhombus tilings that have this property that are symmetric with respect to this symmetry axis, and for example this is symmetric. In that case, if I want to count all of them, then I can throw away one half of it because it doesn't tell me anything, so I have thrown it away. And now again I introduce lattice paths, and now the situation is slightly different. Again, you have fixed starting points along the lower side, but where these rhombi that stick out of the symmetry axis are, this can be anywhere. So what I have to do now is, again, if I do the conversion to paths on a square grid, then now what I want to do is to count non-intersecting lattice paths which have fixed starting points, but where the endpoints may be anywhere along this line. So the endpoints are not fixed, they are in a given set. So this says the same thing. Given starting points, n of them, endpoints, and we want to count families that have these starting points, and every path ends in one of these points. And here's the corresponding theorem of Okada and Stambridge. It tells you that the number is given now by a Pfaffian. So in fact, I'm cheating slightly because for this theorem I have to have an even number of lattice paths. If you have an odd number, then there is a trick to convert this into just add an artificial zero-length path so that you can apply this theorem. So it's a Pfaffian. The entries of the Pfaffians, they are slightly more complicated. It's a double summation over certain path numbers, but again, it's explicit and in principle you can use it. There's again a weighted version of this. The proof of this again uses this switching idea. And in our problem, if you write down the Pfaffian, here it is. And George Andrews proved about 30 years ago that the number of vertically symmetric rhombus tilings of a hexagon with these side lengths is again a very nice product formula. In this formula I use the notation for rising factorials. This alpha with index n is alpha times alpha plus 1 times and so on up to alpha plus n minus 1. So again, George Andrews didn't know anything about rhombus tilings. He was talking about symmetric plane partitions, but it's totally equivalent. And there are now several proofs of this theorem, but none of them is very easy. So what about some fixed and some variable endpoints at the same time? So clearly again there's the question, does this really appear in nature? Okay, so here's an example of this. So now we take a half hexagon. We allow that some rhombi stick out of this line here, and we punch a hole of size 2 somewhere along the horizontal symmetry axis of this region. And again, I introduce paths. I do the same game again, and we get the following enumeration problem. We have given starting points. We have 2 endpoints. These 2 endpoints, they come from the hole, a triangular hole. So these 2 endpoints must be endpoints. And the other endpoints may be somewhere along this line. So this is really now this mixed case. Some endpoints that we want to have and other endpoints that can be somewhere. And again, there is a theorem, in this case due to Stanbridge, that works in that situation. And it says that the number of non-intersecting lattice paths that connect the starting points and the endpoints in the way I've described is again given by a Pfaffian. This submatrix Q is the same as before in the theorem of Okada in Stanbridge, and H counts the number of paths from starting points to the fixed endpoints. And so for our concrete problem, we can use this theorem. We can work many, many pages of technical calculations, and we get another of these extremely beautiful formulas, namely the number of rhombus tilings of this half hexagon with a triangular hole of size 2 at distance 2k from this free boundary, as I call it here, is given by this formula. And let us look a little bit closer. So this is again binomial factorials, very simple, and there's one ingredient, this summation here. It's a single sum that is more complicated and that does not factor anymore. And this is a theorem with Mihai-Ciucu, which is pretty recent, and we use this as a starting point for an asymptotic investigation of these things. The last thing that I want to tell is that the theorems, these non-intersecting lattice path theorems that I have shown you, they have a meta formula, which is this minor summation formula of Ishikawa and Wakayama that I want to explain now. So here it is. It's well, it's definitely a little bit more heavy, but let me go through this. What you have is a matrix G, n by P. You have another matrix H, n by Q. Then you have a skew-symmetric matrix A of size P. And then this identity holds here. So what does this identity tell? You take a summation of Pfaffian times determinant, and the result is a single Pfaffian. The summation runs over all n minus q element subsets of the interval 1 up to p, that means 1, 2, 3 up to p. And the notation that I use here is, that's the opposite notation than I used in the condensation formula. So AKK is the submatrix of A, where you pick exactly the rows and columns corresponding to K. And GK is the submatrix of G, where I pick the columns corresponding to these indices GK. So you do this summation, and out comes a single Pfaffian. So I claim that the theorems that we have seen before, they are all special cases of this formula. So here's the formula again, now compressed. I mean, the conditions are compressed. So as I say, all previous theorems are special cases of this formula. To see this, what you have to do is that you make a particular choice for the skew-symmetric matrix A, you take the all-one skew-symmetric matrix A. That means above the diagonal you have ones, and below the diagonal you have minus ones. And then it's a well-known fact, and with a simple fact, that the Pfaffian of any all-one skew-symmetric matrix, of course even order, is equal to 1. So let's make this choice. Then this simply will become 1, and this here will become the all-one skew-symmetric matrix. Okay. And now the Lindström-Gessler-Vienot formula, the formula for a non-intersecting lattice path with given starting points, given endpoints, both fixed, corresponds to the case where P is equal to 0. P is equal to 0 means that and Q equals n. So Q equals n, that means K can only be the empty set, so you have the summation reduces to just one term. P is equal to 0, that means the matrix G reduces to nothing, so that will disappear, and this is what you get. And well, I guess that everybody accepts this, that this is a very complicated way to write the determinant. And so this determinant you should see as the determinant in the Lindström-Gessler-Vienot formula. Once we accept the Lindström-Gessler-Vienot formula, then all the other formulas are special cases of this. I've put the formula back, and so now I claim the formula of Okada-Stanbridge, which is the formula for non-intersecting lattice paths with given starting points and endpoints you may select from some set, is the special case where Q is equal to 0. Q is equal to 0 means that H reduces to nothing, so this will be nothing, this will be nothing, so let's do it. So then on the left-hand side you take the summation over these selections of columns. So again, if you accept the Lindström-Gessler-Vienot theorem, then this would correspond to counting non-intersecting lattice paths with our starting points and a certain selection of the endpoints. And here take simply the summation over all possible selections of the endpoints. And it says that this is equal to 1 Pfaffian, and this is exactly the Pfaffian in the formula of Okada and Stanbridge. And then Stanbridge's theorem for the mixed case corresponds to this formula here. So I'm basically at the end. So I promised you that this will be a very biased survey, and therefore you may object that I left out many things, which is indeed true. In particular, I left out a very important application of Determinants and Pfaffians in Enumerative Combinatorics, which is the Castellan Determinants and Pfaffians for counting perfect matchings in planar graphs. And as I write here, as a matter of fact, these stand at the beginning of this beautiful asymptotic analysis of tilings, actually perfect matchings, models due to Cohn-Kenyon-Probst and Kenyon-Okonkov-Sheffield, for which Okonkov earned the Fields Medal. But this is really the subject of at least another talk, and since there's just 1 minute left, I should better stop here, and thank you for your attention.
Because you have the hyperdeterminants, you know. Yes. So is there any connection to combinatorics or not?
They don't. I mean, in the Cauchy hyperdeterminant?
No, it's a similar this Gelfand or something.
Oh, this is quasi-determinant. This is in a non-commutative setting. I don't think that they do anything here. So again, so maybe one day somebody discovers something, but I'm very doubtful about that. It seems that everything is nice as long as it is one dimension higher than the structure breaks down.
Yes. You showed the formula with many each function there.
Yes.
Do you even try to simplify that formula? Because there are many denominators.
Yeah, there's a lot of cancellation. So I don't think it makes sense to do the cancellation. So already so we raise a certain point, namely in all these formulas there's a lot of cancellation, and there are many ways to write this. And in fact I've shown you, just mentioned this one point, I've shown you Maclaurin's formula. Yeah, I know, but I want Maclaurin's formula. So Maclaurin didn't write this formula. He had a different way of writing this. He used binomial coefficients. So this writing is due to MacDonald. It has indeed a lot of cancellation. It's really a matter of faith. There is no formula that would not have any cancellation. There are many ways to write it, but in all these formulas there is cancellation. It doesn't seem to make sense to try to see how things.
Okay, any other questions? Well, we thank you.